Moving on to the very last PowerPoint set for the entire semester. In this PowerPoint set, we are going to talk about more details regarding time-varying fields. I divided the contents into 4 subtopics. The first one is the derivation of wave equation. Okay? Whenever we're learning time-varying fields, you cannot avoid to understand the so-called wave equation. But don't fear, okay? There's no fear needed. The wave equation is coming from Maxwell's equations. It's compressing the 4 Maxwell's equations into 1 or 2, okay? So it's actually a process of simplification. And usually our derivation would start in the time domain. Okay, so in your mathematical processes and in your result, you would see partial differentiation equations. And usually we're not very good at math, so we will also introduce the so-called time harmonic fields. Time harmonic field is converting the wave equation from time domain into frequency domain using phasor notations that we covered in the very beginning of the semester, right? But these two, the wave equations, usually under the assumptions, cannot really tell you how the waves are generated. These 2 equations only tell you how, well, if you have a wave already, and how this wave propagates in certain spatial region. That's it. So my personal preference is to isolate one subtopic, which is called the inhomogeneous wave equation, so that you can understand and appreciate how waves can be generated, right? So this is really not covered in the textbook. I searched everywhere. Usually textbooks do not contain this subsection. So this is extra, and probably all the other professors do not really care, but I do, okay? So after understanding how the waves can propagate and how the waves can be generated, we want to focus on one particular type of wave. You can have lots and lots of wave formations or different profiles, but usually we want to stick to the plane wave, okay? If you understand plane wave, basically you understand everything, okay? The reason will become evident later, right? So today, let's first look at the wave equation, how to derive it, and remember, to differentiate how to generate waves, I called that equation inhomogeneous, and therefore, for the common type, the conventional wave equation is the homogeneous wave equations. Okay? We first start from the time domain. Okay? This is again Maxwell's equations. The 4 equations, only this one is really modified by Maxwell. This is the displacement current density, which we talked about on Monday in details. The need to include this term is to explain the physical meaning, how a current can really be conducted through a capacitor, and also mathematically to avoid conflicts for the null identity. Okay? So this is Maxwell's contribution, but eventually all 4 equations, Faraday's law, Gauss's law, Ampere's circuital law, are all coined under his name. Okay, so as you can see, we have time derivatives, right? Here, Faraday's law and the modified Ampere's circuital law. We have time derivatives. That means we are working in the time domain, right? If you're not working in the time domain, you do not see this time dependence explicitly. right? So up to now, up front, all the 4 equations that you learned in the past in this form are actually in the time domain. So these fields are time dependent and spatially dependent. Okay? So these fields are spatially dependent and time dependent. Therefore, you have the time derivatives. And up front, usually the derivation of the wave equation requires a set of assumptions. So today I'm going to spend a lot of time to walk you through what these assumptions mean. Okay? First assumption, you have a wave. You have a wave already. That's the first assumption. You have the wave. And this wave is now propagating in a simple medium. So think about it. What does a simple medium represent? I'm a very nice teacher. I'm telling you the answers, right? A simple medium, the simplest medium that you can think of is a linear medium and a homogeneous medium, and it is also isotropic. So all these 3 behaviors are showing up at the same time, and that is called a simple medium. But that's not really explaining anything, right? That is trying to use 3 more terms to explain 1 term, right? So if I'm a very irresponsible professor, that's it, let's move on. But to show you I'm very sincere, I'm very devoted to teaching, let's talk about, okay, so simple medium can be divided into, first one, linear. Second one is homogeneous. Let me just write homo. Okay? And third one is isotropic. Okay. Can anyone tell me what do they mean? I mean, just looking at the word, you know it, right? Linear means it's linear, right? But what is linear? When you use the word in linear, what are you talking about? What or which 2 field quantities are you trying to relate so that they have a linear relationship? Otherwise, the word in linear is still useless, right? Homogeneous. Do you know homogeneous, this word? What does it mean? 均匀, very uniform, okay, very uniform. Isotropic. Usually, Taiwanese students do not know this word, so I'm just wondering, do you happen to know what this word means? 等向性, meaning that this material responds in the same way no matter which direction your field is oriented. Okay? So this is having certain direction. And this is telling you how uniform your material is. And this is telling you, well, maybe 2 fields are interrelated in a linear way. So still, I mean, after all those explanations, you still don't understand. Okay? So what about, let me just write. Linearity in electromagnetics is trying to reflect the truth, how a material responds, right? If you still remember, up to now, we only covered two responses, right? You have a field, externally applied field, and you have material. Material reacts to this externally applied field by generating induced dipoles. This dipole can be electric dipole or magnetic dipole. So if you have an electric material, you can create dipoles. And how many dipoles you can create is coined, right, by the single parameter epsilon. Also at the same time, you have B equals mu H, right? If you have this material also has magnetic properties, it can generate induced magnetic dipoles. And that ability is coined by this mu parameter, the permeability, and this is permittivity. Up to now, what have we assumed? D and E are interrelated in a linear fashion, right? So this term multiplied by this term is in the same order, right? So D is directly proportional to E. So this is telling you D and B is directly proportional to E and H. So that's called linearity, right? Well, you can have potentially D equals epsilon E plus epsilon double prime E squared, right? Potentially, I mean, if you really want to investigate into real materials, this is the linear term. And these and the terms after it are the nonlinear terms. So these are called the nonlinear terms, right? If you don't care about this one, this material would give you a flux density that is proportional to the square of your input field, right? So this is a nonlinear material, okay? And if you are dealing with nonlinear material, it's a complicated process. So you are not dealing with a simple medium, right? So I'm giving you the definition, and I'm giving you a counterexample, all right? Okay, let me erase this part. Second assumption, homogeneous medium. Well, homogeneous medium, do we need to write a new set of the material response? Think about it. In the two equations I just wrote down, D is equal to epsilon E, B is equal to mu H. These two equations, although I mentioned they are linearly related, but at the same time, I also made a second assumption. I'm now dealing with a homogeneous, a uniform material. This wave, all these field quantities are traveling in a homogeneous medium. Why? Because epsilon and mu are viewed as, tell me the magical word. Here, epsilon and mu are both constants. Thank you. Why can they be treated as constant? Because you have a medium that is so perfect, so well behaved, so that in the entire space, location by location, they give you the same response. Okay? This is called homogeneous medium, and this is called inhomogeneous. Okay? For example, let me give you an example. You have a wave propagating from the left to the right, but now you have material 1, material 2, material 3. You have different materials, meaning that you have non-uniformity, right? You can no longer use a single epsilon or a single mu to perform these derivations. Okay? Or inside one medium, you have patterns. All these patterns are made of a different material. Then you cannot use a single constant to describe that medium. Okay? Homogeneous medium, you have the fortune, you have the good fortune to use a constant to express the material properties, epsilon and mu. Okay, third one. Whenever you have questions, feel free to raise your hand and stop me and just ask. Okay? Third one. Isotropic medium. Well, I explained in Chinese, it's 等向性. It's how this material is responding to the fields when the fields can be oriented in different directions. But what does that mean? Well, we know that fields, all these four fields, are vectors. Vectors come in amplitude and directions, okay? So you might have an E field. You might have an E field. This is called E1, right? So this E field is polarized or oscillating in this direction only. Assume. Now, in the same material, E1 is polarized in this direction, and it sees epsilon 1. Right? When you orient your field in this direction, you have your potential to create electric dipoles, right? But what happens if you're E2, you can just rotate this field direction. So now that the E field is oscillating in this direction, well, that is possible. But what happens if the same material, the material is the same, you're only changing the orientation of your field oscillating direction, and magically you have epsilon 2. What does that mean? For the first one and second one, pretty much you can imagine. But this one is really, really new to you. But it's very common in optics. I come from an optics background. So this is very common for me. But just think about it. What is epsilon? Epsilon, that single perimeter, captures how good this material can produce induced electric dipoles, right? So now this fact is only telling you this material, okay, if I'm telling you they are having different values, and I also tell you that epsilon 2 is greater than epsilon 1. If that is true, what does that mean? In physics, what does that mean? It means this material can produce more electric dipoles when your external field is aligned in this direction, right? So E2 is D epsilon 2. Assume D is your externally applied field. When your epsilon 2 is bigger, then actually E2 is weaker, right? So this is an anisotropic medium. It responds differently to your field direction. So this is anisotropic material. You add An before it. Okay? Now think about it. Mathematically, how do you describe an anisotropic medium? So let me erase this part. D is still related to E linearly, and we still assume this medium is homogeneous. So epsilon 1 and epsilon 2 are still constants. They are not spatially dependent. But here, I need to use a tensor, right? For example, epsilon 1, epsilon 2, epsilon 3, 0, 0, 0. That's the easiest one, right? This is telling you when your E field is polarized, or here, X, Y, and Z, okay? So when your E field is aligned in the X direction, it gives you, well, okay, in this way, 1, okay? When your E field is polarized in the X direction, this material gives rise to epsilon 2. And when your E field is oriented in the Y direction, it gives rise to epsilon 1. And maybe when your field is polarized in the third direction, it gives you the third epsilon. Okay? So to capture this anisotropic behavior, now epsilon is no longer a single constant. Rather, you have 3 different constants. So you have to write them into a tensor. Tensor here is more like a matrix, right? Ideally, you would have 9 terms, but you only capture the 3 terms, the diagonal 3 terms. Okay? So think about it. Again, think hard. Even though all the textbooks are telling you, oh, our wave equation derivation is under the assumption of the wave in a simple medium. And the textbooks would tell you, okay, I have a linear medium, I have a homogeneous medium, I have an isotropic medium, but usually they don't tell you the details. Okay? So I'm telling you the definition of all 3, but I'm also telling you the counterexamples so that you can appreciate the derivations are really carried with a lot of assumptions, simplifications, we are dealing with the simplest medium possible, other than vacuum. Vacuum is the simplest one, but we don't really like it because there's nothing much to learn. Okay? So simple medium means linearity. D and E, B and H are interrelated in a linear fashion. And at the same time, epsilon and mu are treated as constant because we have assumed we're dealing with a homogeneous medium. And probably the strongest assumption is this isotropic property. Okay? No matter how your E field or H field is oriented, this material gives you the same epsilon and mu. That is almost, ideal, perfect. Okay? Even air, even water has certain weird direction dependence. Okay? Question up to now. Is it clear enough? Okay? All right. You're smart. All right. So in the future, although we have seen this, we introduced these two relationships in the past, but now that you understand, these two equations were made under very stringent assumptions. Okay? So simple medium is really not simple. Okay? And then further, well, all the textbooks feel that just simple medium is not enough. We want to give you some more bonuses, so we further assumed the medium that we're dealing with is charge-free and non-conducting. Well, for these two conditions, you should be able to tell yourselves, source-free, which term are you trying to knock out from the Maxwell's equations? Charge-free, non-conducting. Charge-free, here, all you see that is related to charge is rho, right? So you're further assuming here, in this medium where the wave is propagating, we have no free charges. Okay? Non-conducting, you have no free current density. Further knock this one out. Okay? So after all these simplifications, Maxwell's equations is reduced to a very simple form. So Faraday's law is now reading curl of E is equal to the negative mu h, and h you're trying to find its time derivative. We simply replaced B equals mu h. Okay? But you are able to write it because this mu is a constant, so it's a homogeneous medium, and it's a simple constant because this material is isotropic. Okay? And it's having a linear relation. So the second equation, Gauss's law, can now be written as divergence of E is equal to 0 because rho is 0 and D equals epsilon E. But since this is 0, you can just divide epsilon out. Okay? Modified Ampere's law is now without the J term, without the free current density. Okay? Gauss's law for magnetics, divergence of H is equal to 0.